The eyes of the dead reacted to the light. Scientists have brought photosensitive cells back to life. Scientists have revived the light-sensitive neurons in the eyes of post-mortem organ donors and restored communication between them. This is part of a larger series of experiments that could transform brain and vision research. These studies also offer new opportunities in transplantology and question the irreversible nature of death. Billions of neurons in the central nervous system transmit sensory information in the form of electrical signals. In the eye, specialized neurons called photoreceptors sense light. A team of scientists from the Ophthalmology Center of John A. Moran at the University of Utah and researchers at Scripps Research used the retina to study how neurons die. They also tested new methods of reviving them. We were able to awaken the photoreceptor cells in the human macula, which is the part of the retina responsible for central vision and the ability to see fine details and colors, explains Dr. Fatima Abbas of the Moran Eye Center, lead author of the study. In eyes taken up to 5 hours after the donor's death, these cells responded to bright light, colored light, and even very faint flashes, he explains. An article describing the research was published in the journal Nature. While initial experiments allowed the photoreceptors to be revived, it turned out that the cells had lost the ability to communicate with other cells in the retina. The team identified oxygen deprivation as the most important factor leading to this loss of communication. To solve this problem, Professor Anne Hanneken obtained the donor's eyes less than 20 minutes after death, and Dr. Franz Winberg designed a special device that restored oxygen and other nutrients to the donor's eyes. Winberg also constructed a device to stimulate the retina and measure the electrical activity of its cells. Thanks to this team, they were able to recreate a specific electrical signal found in living eyes, the B wave. This is the first B-wave record from the human retina after the patient's death. We were able to get the cells of the retina to talk to each other the way they do in the living eye, mediating human vision, says Winberg. Previous studies have restored very limited electrical activity in the eyes of organ donors. But this has never been achieved in the macula to the extent that we have now demonstrated, emphasizes the scientist. The process demonstrated by the team can be used to study other neural tissues in the central nervous system. This is a groundbreaking technical advance that could help scientists better understand neurodegenerative diseases, including retinal diseases such as age-related macular degeneration. Winberg points out that studies on eyes taken from the dead are qualitatively better than those performed on animals. Although mice are commonly used in vision research, they do not have a macula. Researchers can also test potential new therapies on functioning human eye cells, speeding drug development. The scientific community can now study human vision in a way that is not possible with laboratory animals, says Winberg. We hope this will motivate organ donor associations to understand the new and exciting opportunities that this type of research offers, he emphasizes. And these new possibilities are really exciting. The researchers' achievement is of great importance in transplantology. While organs such as kidneys or liver can be stored for many hours from the moment of collection from the donor, the tissue from the central nervous system dies almost together with the person. Restoring eye function after donor death gives new hope to all those waiting for a transplant. Hanneken, who is also an experienced eye surgeon affiliated with Scripps Memorial Hospital La Jolla, said the ability to produce viable patches of human retinal tissue could accelerate the development of new treatments for diseases that cause blindness. Until now, it has not been possible to make harvested cells from all layers of the retina communicate with each other in the way they do in a living retina, says Hanneken. However, in the future, we may be able to use this approach to develop treatments to improve vision in people suffering from macular diseases such as age-related macular degeneration, he explains. Monkeys start and end interactions just like humans. Starting interaction between people usually starts with saying hello. A similar courtesy in the form of a goodbye is also used at the end of the interaction. Until now, scientists believed that we were the only species that used such treatments. But as it turns out, some of the primates have similar behaviors. New research has revealed that common chimpanzees and bonobos have their own way of saying hello and goodbye, using special cues to start and stop interactions. When we're talking to the other person, we probably wouldn't leave without saying goodbye because that would just be rude. As it turns out, some primates also have a habit of maintaining good manners. In a new study, scientists have been able to document the intentional signals of common chimpanzees and bonobos to start and end interactions. These are behaviors that have so far only been observed in humans. The researchers also found that social changes and power dynamics among the apes affected the communication efforts used. Researchers believe that such behaviors reflect patterns similar to human gestures of kindness. We were able to build rockets and land on the moon because we have the ability to share our intentions. This allows us to achieve goals much more complex than a single person would be able to achieve. This ability is believed to be at the core of human nature, explains Dr. Raffaella Heason of Durham University in the UK. Sharing intentions and working together on a specific goal leads to a mutual sense of duty, which experts call joint commitment. Dr. Heason and his team have spotted signals in the great apes that could challenge the current theory that shared commitment is unique to humans. Their research was published in the journal iScience. In previous engagement experiments, human babies protested when the experimenter suddenly stopped playing with them by offering toys or vocalizing. The children tried to re-engage the experimenter in the previously agreed-upon play. A similar situation was observed between two bonobos who had their play interrupted. The animals then used gestures to resume interacting with each other. Following this discovery, scientists began to wonder how and when collaborative commitment first appeared in humans. In contrast to previous research, Dr. Heason and her team have proposed a slightly broader understanding of shared commitment. They assumed that it is not only based on a sense of obligation between two participants to meet a common goal, but also involves the process of creating an agreement and mutually deciding on its fulfillment. This means that something as simple as making eye contact and saying hello and then signaling the end of the conversation can be an example of this process. So Dr. Heason and her colleagues set out to see if great apes use similar cues to start and stop interactions. The team analyzed 1,242 interactions in groups of chimpanzees and bonobos in zoos. Researchers found that the great apes did indeed glance at and communicate with each other frequently to start and stop interactions. Bonobos exchanged start signals and mutual glances before starting play 90% of the time. Cases, and chimpanzees in 69%. End of activity interactions were even more common, occurring in 92% of the cases. Bonobos and 86%. Chimpanzees. The cues included gestures such as touching, head-to-head or holding hands. The monkeys also stared at each other before and after interactions such as grooming or playing. The researchers also took into account other factors, including how closely the monkeys knew each other or which had more power over the other. Interestingly, the more closely or related the bonobos were, the shorter the duration of their entry and exit phases. The authors say this pattern is similar to how we humans communicate with others. When we're interacting with a good friend, we're less likely to put a lot of effort into polite communication, explains Dr. Heason. However, the level of familiarity and the strength of social bonds no longer had a similar effect on chimpanzee interactions. This may be due to the fact that, compared to the despotic hierarchy of power in chimpanzees, bonobo communities are considered more egalitarian, due to existing friendships and alliances between females and close mother-son relationships. In terms of understanding the origins and evolution of shared commitment, this study is another step forward. However, Dr. Heason points out that there is still a lot of work to be done. Behavior is not petrified. You can't dig up bones to see how behavior has evolved. But you can study our closest living relatives, apes like chimpanzees and bonobos, argues Dr. Heason. The author would like to conduct similar research on other anthropoid species in the future.